then we're going to generate a bunch of new functions by taking this new variable x of t plus 1. So this doesn't show up in any of these variables. And taking this, and so we're going to basically do this process in reverse. We're going to take two functions from this pool and add them together in this fashion and get a new function. Now, some of these so we refer to this as a conjunction over x of t plus 1. Now, some of the resulting conjunctions that we get are going to have degree 3. Others are going to have degree 2 or less, maybe even 1 or 0.
Also, they won't all be Boolean, will they?
What? They will all be Boolean.
Oh, wait.
Yeah, because we notice that just as this taking apart process produces a Boolean function, two new Boolean functions, conjoining two Boolean functions gives us another Boolean function. Since if we output, we're plugging in everything is equal to 0, 1. If it equal to 0, we're getting the output of a Boolean function. If 1 is out, we get an output of a Boolean function. If it's equal to 0, we're still getting the output of a Boolean function. So, this process, so this gives us a whole bunch of functions. Some of them might be old, some of them might be new. We take conjunctions of those, and we get a whole bunch of new levels. And iterating this process, we should eventually reach a point where a new level of conjunction doesn't add anything we haven't seen before. So that seems pretty manageable. So we take the conjunction of these guys, and let's say that there are a couple hundred in here. That'll give us like 100,000 functions over here, and then when we take the conjunction of these guys, we need to do like 10 billion. Okay, nope. So unless we want to wait a year and a day for our program to compile, we need to do something else. That said, so let's take a little look at the way in which we define conjunction again, and take a closer analysis of the degree and maxonomial hitting set size of our output. So, what happens if we plug in two functions of two functions that are of f1 and f0 in there, of different degrees? Well, the degree of our resulting f is going to be 1 greater than whichever the bigger of the two is. Same thing if they have the same degree, unless they have exactly the same set of maxonomials. In which case, all the degree d plus 1 terms in here will precisely cancel with the degree d plus 1 terms in here, and we get a new function which has the same degree as the output, as the original set. Except its maxonomial hitting set size will be 1 bigger.
So John, what your goal now is to try to take this?
What? We're trying to see if this still holds for d equals 3.
Yeah.
So, great. So let's maybe some of these.
For 2 and I wanna prove it for 3.
Yes. So, maybe we can take some of these conjunctions and maybe some of them aren't necessary. So let's see what happens if we take a conjunction of two things of degree 2. We get something we already found. So we're not going to get anything new out of these guys. What if we take a conjunction of something of degree 2 and degree 3? Get a function of degree 4. So clearly, you guys are stone cold, useless. You're already up here. We're not gonna get anything new via conjunction with you guys. Let's just ignore you for the time being. So now, we've got just the degree 3 functions. You notice they all have maxonomial hitting set size 1. However, if we take the conjunction of two things that have a different maxonomial set of maxonomials, we're going to get a degree 4 function. So we only need to check, if we treat each of these little pools as the set of functions that have a given maxonomial hittings, a maxonomial set, we're only going to need to check conjunctions within that pool. In addition, if two pools have equivalents, have isomorphic sets of maxonomials, so there's some way of reordering the variables and toggling it so that it ends up, the maxonomial set ends up the same, well, we only need to check one of those. Since all the descendants of one of them are going to have corresponding descendants in the other. So that makes our time to run a fair bit more manageable. And so we'll get new functions. Some of them will have been repeated, show up here. They'll be ones with maxonomial hitting set size 1. And we already are working on what those guys' descendants look like, so throw that out. And we'll just have h plus 1. And iterating this process, we see not only does this eventually give us the number of functions, all the degree Boolean functions, it also does so in a very natural way to figure out what the maximum maxonomial hitting set size is. So the one question we're left with is, how many variables? Well, here we can once again use the fact that descendants, so to get our descendants, we're only going to conjoin functions that have the same set of maxonomials. So when we conjoin two degree 2 or less functions, each of them has at most 4 variables, so the resulting conjunction is going to have at most 9 variables. 8 from here, and the 9th one right here. And in addition, all of its descendants via conjunction are going to consist of that same set of variables, plus whatever gets added here. In any case, it seems that we need at most 8. Almost. Because there's one complicating factor. What if a variable doesn't show up in a maxonomial in one of these guys? So, such a variable that's in a degree 3 function that shows up in the function but not in a maxonomial, we refer to as an orphan variable. However, one rather nice thing that falls out is that no function has more than one orphan variable. The only ways in which we can get an orphan variable is either we're conjoining a linear function and some quadratic function that doesn't involve that same variable, or by conjoining two things that have exactly the same set of maxonomials for one variable, one of their variables. However, it's pretty easy to see that there's only one way to take a conjunction that involves a total of 8 variables. And that's by conjoining 2 disjoint cases of this function, which we call rings. So there we won't need to, in that case, we won't need to worry about orphan variables. In addition, for every smaller case, any given function is going to have at most one orphan variable. And each orphan variable is going to show up in a quadratic term. So if we take the product of two functions that each have, not the product, the conjunction of two functions that each have an orphan variable, well, then neither variable is going to end up being orphaned. So in other words, to get the full set of functions of the isomorphism, having our 7 variables actually showing up, plus 1 for an alternate orphan variable is sufficient. And so we see that we need at most 8 variables. So running this operation, we hit all the functions with maxonomial hitting set size 1, then 2, then 1 more gets us to 3. And then when we look at conjunctions of those and take out all the things that we've already seen, that i.e. have maxonomial hitting set size equal to 3 or less, we get all the functions of maxonomial hitting set size 4. And ideally, that's empty, and our conjecture is, we show that our conjecture is continued up for 1 more step. There's just one problem. It isn't empty. We in fact find this function lurking, waiting to ruin our day. This particular function, known as contra, which I could refer to as contra, is a counterexample to our conjecture. And so it appears that we can't say that the h of f is always less than or equal to d of f.
So what's h here?
What's h?
Yeah.
Maxonomial hitting set size.
No, so
Here it'll be 4.
yeah, no, I mean, yeah. And d is 3, yeah.
Yes. And it is indeed Boolean. So,
How did you come up with it? Did you come up with it?
generated via essentially this process.
So you were hoping not to find that?
Yes.
Yeah.
But we did, it exists, and well, it's annoying.
So you can add one and take conjecture.
So, our conjecture is false. So, hey, maybe we can come up with it, we can salvage this. Maybe we can have a similar conjecture like h of f is less than or equal to some constant times d of f, where the constant is universal. No, we can't. And the reason for that is because of an operation called composition. Basically, if you can compose 2 Boolean functions f and g by taking, if f is a Boolean function in n variables,
So this warrants much more.
what?
This counterexample warrants much stronger conjecture.
This?
No, this counterexample,
Yeah, breaks.
yeah.
Yes. So by looking at the composition of f and g, this is the function where you take n copies of g on completely independent variables, and use them as your inputs for f. So if you perform this composition, the number of variables, if f is in n variables and g is in m variables, then this composition is going to be a Boolean function in m times n variables. And they'll all continue to be relevant. In addition, the product of this composition, the degree of this composition is equal to the degree of f times the degree of g, and the maxonomial hitting set size is equal to the degree of f, the maximum hitting set size of f, times the maximum hitting set size of g. What this means is that the very existence of a function which has, if we just take contra and we take its composition with respect to itself multiple times, we do this any number of times k, and we get a function with contra f equals contra times composed with contra, composed with and so on and so forth, k times the h of f will be equal to k, and d of f will be equal to 3 to the k. And simply put, there's no c such that 4 to the k will be less than or equal to c times 3 to the k for all values of k.
So even the power alpha, so it's 4, so even if you did even the stronger one with d of t to the power.
Yes.
For 3, I guess.
Exactly. Ah, well, at least it doesn't break. Oh, well, it means we need to adjust our conjectures. We'll get less nice results that can't proof. And hey, this conjecture we haven't disproved yet. Right.
So what can we find a lower bound for the power?
For what?
Which you can provide a compute something. Oh, yeah, it should be lower bound. I mean, if it's not 2, it's like 1.5.
Say again.
I mean, the power would be,
Oh,
yeah.
we don't. So right now we know that if we're going to have something of this relation hold, it better be bigger than
Log 4 to base 3, I guess.
yes.
So this is, so everything is bounded.
It would need to be of the form h of f. We know that h of f is none less than or equal to d of f k for k less than or basically 4.
Thank you very much. Don't forget to answer questions in private. Thank you for being very nice and lucid talk.
Thank you.
And good luck with the weaker conjecture.
Thank you.